Hi, everybody. I'm Ober Demaray. This is Jeff Bell. So we're both authors of the cell materials and battery chemistry sections. The names change every part of basically every year. So what we've always focused on is basically letting people who are not in the industry kind of be able to review different parts of how cell materials and design choices impact performance and how those aim towards different markets or applications. And this year was actually really exciting for several reasons. One, just from 2 years ago to now, this section has grown from 50 pages to about 150 pages. Hundreds of people have worked on this. So, first of all, a big thank you to all the other contributors and authors for this section and the rest of the battery report. And the second thing is that for this year, for the first time, because this has traditionally been a very lithium ion focused report, this section has brought in a lot of other chemistries, including lead acid, which probably should have been the first thing we added originally, but hadn't been added until this year. So there's a lot of things like that we're really excited to share with you. We had to pare 160 slides down to under 60, so we're only going to share a couple of them. Jeff, you want to say anything else?
No, I think that covered it all. But yeah, we're just excited to share all the updates this year, and thank you again to all the contributors. A little fun fact, Aubert and I are new dads, so if we didn't have everybody helping us, we would have struggled real hard this year. So big shout out to all of them.
Okay, so cell design and materials, and we're going to just jump right in. Oh, I'm sorry, Chloe, why don't you say two words about what you're doing afterwards, and then we'll jump right in.
Sure. So I'm Chloe Flower. I'm a patent attorney specializing in chemistry, material science, and energy storage technologies. And my work spans managing patent portfolios and contentious proceedings. I help innovators not only protect their breakthroughs, but also then assert their rights when it matters the most. The section that I'm going to run through, as Aubert alluded to, are the summaries on the patent landscape and litigation trends, disputes in this field, with data that's been provided in the report with the help of NoMade and a few other contributors. So again, many thanks to them.
Okay. All right. Once more, Jeff, take it away. All right.
All right, guys. So this year, kind of as Aubert said, the goal is to increase accessibility. So what we did a lot in this year's report is one, add a lot of visuals to help people better understand some of the trade-offs, but two, we're also starting to add a lot more just foundational information. This is to kind of help the adjacent industries with understanding what's going on. So here we're just giving examples of the function of each of the different components with inside the battery across the various chemistries that we're sharing this year across lithium ion, sodium ion, and lead acid. But the goal here is right is if you are a industry adjacent, you're in venture, you're in utility or something, and you don't have any experience dealing with batteries, or you're talking to some of these startups, the idea here is to get you guys a better foundational understanding, but just help increase clarity. Next slide, Aubert. This one is always a fun one. I would take this is kind of like a bunch of our views, or the view of a bunch of us on kind of how the chemistries are evolving through 2035. This is kind of how we view the projection landscape. Some of these have shifted from last year, and we've also additionally added some different concepts here, right? We have liquefied gas, electrolytes, for example, which is out of San Diego from South 8. So we're adding not only the new chemistry starting to come in, but we're also looking kind of as a projection of their landscape of when we expect them to become relevant. And some of this is going to be either due to just maturity of the science or maturity of the manufacturing processes. But we do try to keep this as updated as possible as things do tend to slip, especially when you're talking about manufacturing challenges.
Yeah. And don't worry, solid state like last year is still 5 years out.
Yeah. The other thing we're doing here too, right, is we're starting to add as again that accessibility thing. We're adding to add definitions, right? There's a spec sheet for all cells. They have a ton of rows on them that have a ton of different things, right? And like a good example of that is calendar life, storage life, and shelf life, right? If I said that out loud, a lot of you would be like, what's the difference? Well, two of them are the same and two aren't. So this is to help you understand like what it is, why it's important, what it enables. right? And kind of give you that information where you're saying, oh, this really helps that, or oh, this really helps that, because a lot of that gets lost when you get sent with a spec sheet, right? People tend to throw around watt hours per kg or watt hours per liter, but there's a bunch of other specs that really matter in the cell, and a lot of different applications really focus on that, not all of them.
Yeah. One thing again that we try to focus on is people that are coming in from one particular direction. They work on a carbon material or they work on a equipment type or a process or a QC technology or they're an end user of something. Um, just helping them understand a little bit more about kind of how all the pieces come together and how people in the battery industry talk about stuff and what they kind of focus on and how that kind of propagates from the initial materials to the designs to the battery to the application in the end market. And just the language really matters. And that's something people get lost in quite a bit.
Yeah. Another thing we've added this year, this is geared at mostly academic/industry. I think Ober and I talk about stuff a lot, and whether it's a materials issue or a cell design issue. So for example, a great context is like power delivery. Some materials are inherently better at high C rates, but it doesn't mean you can't tailor a design to hit those C rates with a different chemistry. So what we did this year, and this is kind of just like a smattering of different anode/cathode pairing combinations, is we've actually created a reference design table spectrum. This here is all hyperlinked in the link below to the different places where these values have been found. But the idea here is you can kind of look in now and see kind of the range at which different cell designs exist for different anode and cathode pairings, right? We have like LFP graphite, LFP silicon, which is weird, but Coreshell does it. So, that's kind of like why we have it there. We tried to keep it relative to people who are actually doing things, right? NMC lithium metal, NMC silicon, LMR, right? Lots of things, different of the different sodium ion chemistries, and they're all here to kind of be represented as their different design range. And there's a bunch of other columns. It's just that they don't all fit on this slide. So you'd have to click the link. But like, for
Yeah.
example, copper current collectors, aluminum current collectors, separator thicknesses, all that stuff is loaded elsewhere. But this here is pretty good starting point for anybody who wants to start saying what is kind of the average cell design or the range of cell designs we expect to see for a given chemistry based on what's available today. Here, this took a lot of work, but this is basically here to show kind of the different impacts, right? I think there's a lot of different prismatic team, cylindrical cell team, pouch cell team, and kind of what they bring to the table. Here is just kind of to show you across different designs, the impact of those different form factors on the overall design space of cells. And kind of the key takeaway here, right, is pouch, due to a lot of reasons, is going to exceed a lot of different chemistries. That's one from a packing efficiency point of view, but also just material thickness and weight. And then you're going to see cylindrical and prismatic a little bit lagging behind on the back end. And this is across, I think, every chemistry you see in the design table. There's about 404, no, when I ran this, there was 16 million designs that were generated and plotted on this graph. My computer almost bricked itself as a result. But this kind of gives you that entire design space across different form factors and what they expect to look like. And if you go to the
And
next slide,
again,
oh,
I
oh,
was,
go
I was
ahead.
going to say real quickly that this is also cell level. And so,
Yeah.
one of the big trade-offs for these is sort of stability, form factor, and safety versus energy density. And of course, pouch cells, you have to do a lot more on the pack level to get them to be equivalent from a safety, from a thermal management perspective, from a structural perspective. And so this is cell level and where they're kind of typically much farther ahead. And then sometimes on a pack level, the other two either catch up or even get ahead.
And that could be anything from voltage to you name it, dealing with the space. This kind of flows into the next slide where I've actually broken up all the different design spaces by all the different chemistries that were in that table, and kind of plotted them out in the different form factors on the top. So you're getting kind of where these things exist in a range and where they're kind of expected. As you can kind of see, they have very different curves associated with them, and that's just a function of the form factor bringing either some inherent inefficiencies or some inherent benefits, right? So like pouch, you're going to see everybody likes to show the pouch graph because it's got the biggest numbers, right? Prismatic and cylindrical are going to be a little bit less. And just for context here, prismatic is a wound in these designs. It's not a stacked. The numbers, the shape will change if it's stacked, but I only had so much time to create different models for different types of cells. So this is all here, and the goal here is to just kind of share it. The next thing here is, go ahead, over. The next thing here, and this one
Um,
is really fun, and credit to some people online who took this picture. But the idea here, right, guys, is as we look at different chemistries, there's a clear advantage in volumetric space that is hard to just see as a number. So this is really there to kind of like show the impact of LFP with the ref same form factor, and then moving on to kind of like a big NMC cell, right? So there's huge differences in overall size and volume these cells take up, and this also shows you why people are moving to just bigger batteries because it just saves you space. Aubert?
Okay, great. This is an update on something some of you have probably seen in previous years' reports. Jeff and I have been doing this since 2021, and basically updating it every year with feedback, either adding more, and just real quickly, to jump through the other ones before I start on this. But basically, it maps out a lot of different, primarily lithium-ion cathode variations against anodes, and then some of the other competitors, sodium-ion, lithium metal, solid-state lithium sulfur. This one basically gives you all of the different material variations and then kind of their different performance metrics with a little bit of a qualitative color grading. And what that maps down to then is the same ones into different applications and sub-applications with kind of what the priority of most important performance aspects for those applications are, and some market size data, which we couldn't find good ones for 2025. So these are from 2024, still from the previous year. And again, with kind of grading of best and worst for some of those different things. And in a lot of cases, really people just buy what is good enough and cheap enough. And so what these are really meant to illustrate more is what they want. What's most important? What might you get a premium for? What might you lose an order for if you can't hit that metric? And then it drops into a couple more things to look at it a little bit differently too, but I'm going to go back to the first one. Um, so this is something that we've maintained a lot. The entire set of spreadsheets is all on the battery application breakdown, which you can go to from the report. You can see all the ones from the previous years too, if you want to see how they've improved. Um, in general, some of the newer chemistries are higher energy density and then have worse other attributes, typically safety, cycle life. And when you flip them to the other side of the ones that are kind of winning right now, really LFP in many cases is the current market leader, and it's really just because of the cost. And it's safe enough, it has very long cycle life. And so what you end up getting is kind of a cumulative metric where dollars per watt, basically dollars per kilowatt hour per cycle becomes the actual metric that people want for things like BESS. And so there's a lot of nuance to these. I hope you guys enjoy looking at them. If you disagree with something, please send us comments. And again, same thing for the market matching, trying to look at not necessarily what people use today, but what they want from a performance metric and grading each of the chemistries on that performance metric. Jeff, you
Yeah.
want to talk about this new one?
Yes. And then kind of as we've done those, what we've realized or as we've evolved in our thinking is that the reality is each of the markets really have priority categories. You can basically break down any application into what the customer is paying for, what they might pay for if there's a tie between them and another cell, and then what they aren't paying for, right? So like for example, like a good example is max charge pulse isn't really a huge thing in like residential. Just doesn't really matter to them as much. But the goal here is to kind of just say across these various metrics, here's what these applications care about the most, here's what they really don't care about, and here's kind of where the tiebreakers are. And if Aubert, you go to the next slide, as we evolve this section, we've actually paired it up to the different chemistries you saw early on, the different designs, and then kind of who's doing these really well, who's not doing these really well, and kind of where those should be headed. And the idea here is now we're seeing a more, to some degree, still quantitative, but a more directed effort in how we approach it in terms of matching these things to what's going to matter at the end of the day, which is what does the actual application need from a specific characteristic or performance point of view, and then kind of what chemistries hit those boxes or don't hit those boxes. All
Okay,
right.
so now we're going to dive into the materials. Just real quickly, as an overview, again, we took about 160 slides, pared them down to about 60. Most of those, I think 40 to 45 of them are still in the lithium ion through lithium sulfur section. And then we have 5 to 10 solid state and 5 to 10 sodium ion. So in the interest of time, we're going to have like 10 to 30 seconds or less per slide going forward, Jeff. So do you think you and I can do that? I think we can.
Yeah, I think we're up for the challenge.
All right.
Um,
So cathode introduction. Again, one of the focuses this year was not to just have everything be lithium ion focus or equivalent lithium metal solid state, which is what we've done before. We now talk about also other types of materials. This is back on lithium ion focused mostly, but again, just what cathodes are, how they work, what matters, what do they influence, why do people pick them? Um, there's some amazing slides by one of the contributors, Shinron, who's been doing this for 2 years now on basically the voltage of the cathode, which is actually critically important in why people pick those materials and in cell design. And this is one of a couple slides she has on why that matters, how it works, how the different materials impact that. Some really good stuff there as well. And continuing on that, why people use NCM versus LCO versus these other cathodes and how that impacts the energy density and the voltage ranges.
Yeah, and we're also starting to add in kind of like the latest trends in a more microscope point of view, right? Layered electrode architectures that are emerging where they're combining LFP and NMC, CAM processes for dry, like solid state batteries, basically dry cathode for solid state batteries, things like that, where you're seeing the markets kind of shift in general to what they're doing with that material today.
In general, what Jeff and I took out for each of the sections, and again, we need to go very quickly through these, is we left the SWOT diagrams and maybe one or two other things in each of the sub chemistry sections, and we took out the supply chain pieces and we took out the sort of timeline partner company pieces because those take way too long to go over. So again, NMC. Higher energy, strongly used in applications like EVs that need a longer range, still used in some other applications. Um, Mostly having been replaced in commodity batteries at this point by LFP, but still, I think it's 10 to 15% of the batteries still use that. NCA also still used the same way as NMC. Little different trade-off in material usage and cost and performance. A lot of Panasonic and Tesla batteries still use NCA, and a few other makers also still use them with some frequency. NCMA is basically an addition to that that's people have been working on right now to basically lower cost and raise the energy density by adding the manganese. A lot of things you'll see are basically how do we stop using cobalt and how do we use something else that is cheaper and more available without losing out on as much of the performance, at least as much of the performance as they can still save.
Mhm.
Jeff, you want to start?
I mean, LCO has been around for a long time. It's going to be one that's going to be hard to replace, especially in the electronics industry, and that's just from a qualification point of view. There's just a ton of data. But AI, smartphones, wearables, you're going to see a lot of LCO. It's going to be around for a while. It's also a very well understood chemistry, which is why a lot of people like it. As we tend to see these other chemistries come online and have a lot more of a maturation date, we're going to be starting to see LCO potentially phase out of some things, and maybe introduce the others. Keep going.
And for people that aren't chemists, again, for LCO, it has higher voltage and it has a higher stability at higher voltage, and that's really important for consumer electronics.
Yeah, LFP, this one would be beating a dead horse. Basically, it is the commodity battery of today. China's hitting a ratio now of 60% LFP production versus 40% NMC, just to kind of show you where the market is headed in that direction. Strength, basically, it's got one of the best total energy delivery of any cell, and that's basically energy per cycle over total cycle life, right? It's got higher safety. I'm going to say relatively higher safety, because it's not.
Less unsafe, Jeff.
Yeah,
Come
less
on.
unsafe. Let's be real. If you have a car with 100 kilowatt hours in it, no matter what, if you put like enough through it, it will go. But as in everything else, right, it has a lot of like weaknesses, right? Some of it's related to cost variability due to the supply chain, some of it's related to the temperature that it's operating at, right? And then some of it's related to just what applications actually need. LFP is a great all-rounder, but it's not going to fit a lot of the niche applications, which is okay.
And again, the reason it's winning is because it ends up being the commodity battery of choice, which is where cost matters. And so again, it's dollars per energy per cycle. So for the lifetime of a product that needs a longer cycle life, 10 years for a car, 20 years for energy storage systems, it's currently the winner.
It's the Toyota
Uh,
Camry batteries. Um,
MFP again, looking at NCMA is trying to look at how do you add manganese to extend higher energy density without losing the other properties that make LFP so appealing, which again is cost, safety, and cycle life. It does tend to impact those negatively, but it does have a significant impact on higher energy density, which is why people are working on it. So that's kind of a new emerging chemistry that people are seeing more and more. Here again is some nice comparisons of that where you can kind of see the differences as you go from LFP on one side to LMP on the other side with the manganese in the middle. You can see the voltage range shifts this way, and you can see that the energy shifts. So very, very interesting on kind of how you optimize around that. A lot of people working on this right now from a cathode perspective.
And one other thing to kind of take into viewpoint, guys, here is we talk about a cell, we talk about the capacity as a holistic thing, but in reality, when you're talking about an application, there's the usable energy of the cell before you run into kind of like a BMS headache where you have like huge voltage sag. And kind of as you see the manganese versus iron at the top, you do shift that voltage up, as Aubert was pointing out, but the usable energy, as you can see, is the area under the plateau. You hit a sharp decrease in voltage a little bit earlier, right? And that's going to reflect in how the application behaves and how the BMS behaves. And so these are all things that also get taken into account when you're designing these cells.
Okay. Not much to say about LMO. It's an option for chemistries. People still look at it for a cheaper option, but in general, it doesn't have the cycle life or energy density to go with that cheapness to be used broadly. There are still applications for it though.
Mhm.
Um, and then for the third slide, adding basically the LMNO now. So for this, instead of LMO, right, you're adding the nickel. Again, same thing. You're changing the voltage and you're changing the energy density with a cost add.
Yeah, I guess real quickly on that, or I guess we can go here. The whole reason for the LNMO is just they're trying to push higher voltages as possible. There's a lot of advantage to high voltage cells versus increasing capacity. The voltage is the multiplier of the total energy of the cell to a large degree. The big challenge here really is just going to be electrolyte stability.
Yeah. And
And
and again for both of these, and I'm sorry for not, again, we're speeding through these because we still have oh geez, we have 30 slides left to go, Jeff, in probably less than 10 minutes. So but the thing to look at again is as you're increasing one thing, you're typically decreasing another. And so you look at the spots in the middle, and somewhere in here is kind of that sweet point where you have the higher voltage and the higher energy density, sort of somewhere in between right here, right? Anyway,
yeah.
next. This is again just talking about why people are. Oh, I guess you want to cover this one, Jeff?
Yeah, it's just as you're pointing out, it's just why people are looking at alternatives. A lot of things are right now supply chain based and de-risking that. So you're seeing a lot of new chemistries come up, with the big theme being how is the supply chain local to help reduce those shipping costs and also.
Or at least lower cost. How do you not have to use cobalt and how do you lower the nickel? Because those tend to be the higher cost components. So now we're going to jump into separators. Again, still specifically more towards lithium ion, but a little bit more general for the other components. Function of the separator, basically keep the anode and cathode from shorting each other, add some safety, some temperature stability, a lot of times a high temperature shutoff factor where the pores will close, which will then disable further ion transport and stop thermal runaway events, or at least delay, shorten, decrease explosiveness. Cost and manufacturability are a big piece, and in general, also getting thin enough that it's not hitting the volumetric and gravimetric energy density of the cell as an inactive component, but thick enough to still be able to separate them safety, have the safety benefits, and have the thermal benefits. Um, there are a lot of different things that people are doing for separators, and these are across many different types of cell designs, everything from supercapacitors to, lithium sulfur. A lot of different materials, a lot of different additive manufacturing in terms of coatings, a lot of different work being done into controlling the pores and the pore sizes. A lot of different companies working on these technologies. Now we're going to jump into anodes.
Yeah, so anodes here, right? You got three of them here. We're focusing mainly on two, but kind of the key point here is just to go over what the anodes are and what they do. I think over if you go to the next slide, we kind of get more into the descriptions, right? From lithium metal to what we would call full silicon, and even here we're combining silicon monoxide and pure metallic silicon, and then the graphite silicon. oxide-esque, and then just kind of natural versus synthetic. But again, it's towards that theme of accessibility, better defining everything, better defining their advantages and cons, and kind of laying them out there. Keep going.
Sure.
Here's just basically a pure graphite slide. I won't spend a lot of time here, but the goal is it's a great slide to understand and get informed about the different types of graphites and what their advantages are. For example, synthetic tends to have higher rate capability and uniformity. Natural tends to have higher capacity. That's just a high level kind of quick one.
Okay. A lot of focus on silicon the last couple of years, a lot of different players in the space and a lot of different types of silicon. And by the way, both of these slides were done by the same person whose name I can't look up right now, and I'm embarrassed for not remembering. But he did a really good job this year of updating previous year's slides and adding a lot more specificity, clarity, and making really pretty slides. And I will go find that name as soon as I'm able to move my screens. Um, Again, a lot of work on silicon. I would say, if anything, there's been kind of a pivot towards it, especially in the US, as a alternative to one, Chinese graphite, which we don't have access to, but two, over lithium metal, which, while it does have a higher energy density potential, is harder to work with, more expensive, and less safe. And so even like solid state companies now, in some cases, are looking at how do we use a silicon anode to get close to lithium metal energy density without all the safety issues. So it's been a really big focus. There's a lot of good slides on silicon. We're not showing a bunch of the other ones, but silane processes for things like the group 14 and Scylla materials, some of the other ways you can make it, some of the metallic. Um, Probably should have jumped to this slide before I talked about all of that, but it's a big focus in the industry right now of basically racing towards higher energy density while getting high charge rate, while keeping the costs low without destroying cycle life, which is one of the big problems with silicon generally. Now, we actually have the contributor for this with us right now. I don't know if he wants to pop up and say a word or two. No, sorry to put you on the spot, Arnold. But Arnold Capgras did a wonderful job adding these slides for silicon from a patent perspective. And we focus again in this report a lot on the US, a lot on Western markets, and a lot of startups. But really, the real cell makers out of Asia are the ones with all the patents around silicon. So I don't know if you'd like to say a couple words on this in the next two slides, if I'm not putting you on the spot too much.
Carry on.
It's good. Thank you, Aubert.
Okay, all right. I'm so sorry for putting you on the spot. You're the fourth person on my screen, and I noticed, and so I was like, oh, might as well. Okay.
Thank
But
you,
but, but
Aubert.
anyways, so just showing you these also, again, breaking it up by region, by company, by the types and numbers of patents granted, and by country where they're filing them. It's really interesting to me from a business development perspective, and also, I kind of work in between sort of the cell design and places, where people like Chloe work in legal, where I do a lot of tear down reverse engineering work to basically find IP fingerprints for lawsuits, where I'm doing the technical piece of that. And so I get to kind of see the strategy piece for companies, the R&D technology piece for companies,
Mhm.
and then how their patents impact kind of the legal opportunities to either control the market or enforce when people infringe, which happens quite commonly in batteries. So these were fascinating to me. Actually, these are some of my favorite slides that are new in the entire report this year. So thank you again for your hard work on these.
Thank you
Okay.
for your feedback, Aubert. Thank you very much.
All right, Jeff,
Yeah,
we're
so
at
this
lithium
here,
metal.
I know, and we got like 4 minutes here or 3 minutes.
Okay.
So this is just to go over the history of lithium metal. What it's been around a long time. It's going to cover the problems. Keep going. This is going to go over your strengths and weaknesses, right? Lightweight, high energy density. It is the thing exchanging ions. It gets rid of binder and everything. But, as we all know, limited cycle life, cost associated, manufacturing issues, right? But, there are industries that will take this and take that limited cycle life. Drones is a great example. Lithium sulfur, another new and emerging chemistry, probably the one with the highest ceiling in lithium ion besides lithium air. A lot of potential to basically decentralize the supply chain, but this is coupled with a lot of weaknesses, right? It's got the standard lithium metal cycle life issues. It's got lower volumetric energy density. And then this slide kind of here covers the different flavors, right? Lithium sulfur is not a single chemistry, it is like sodium ion. It has multiple sub-chemistries, and that's just kind of here to help you understand that better and what those trade-offs are.
Okay. So solid state. We've got, I think, 2 minutes for solid state and 2 minutes for sodium ion. We're gonna rush through these. So solid state in general, it has been a rolling dream, I would say the last, 20, 30 years even. The dream of it is to enable safe lithium metal high energy batteries where you basically have in every direction, the spider diagram works wonderfully, preferably with low cost, although I have never, having worked in solid state a lot, nobody really claims that, although people put it in their marketing all the time. So what's really going on in solid state right now is despite the many startups and the long periods of time and the funding going into this, there actually are solid state batteries coming out last year to this year in the market. A lot of them are semi-solid state. What that just means is that they have a solid state component, but a lot of times still use liquid electrolyte to enable the cell to work. There are some wonderful slides here talking about the differences between those, the different types of solid state, what semi-solid state versus solid state means, the advantages and disadvantages of both, which typically the more solid state you are, the more expensive and slow the processing is, and theoretically, the more safe you end up being when it works. The farther you go on the other side, the cheaper and faster you can make it. You still get some benefits, not all, but cost and manufacturability are one of the biggest problems with most solid state materials and chemistries. A couple different versions and the trade-offs. This is my favorite slide in this section. Hype versus reality. And this just talks about a lot of the kind of myths and things people talk about for solid state. I really encourage everyone to go look at these. Things like, do they deliver the highest energy density? Well, that depends on the anode and cathode choices. The solid state material is simply the pieces in between that, the separator, electrolyte, cathode light, anode light, things like that. There's two full slides on that are really great.
Yeah.
There's a lot of different materials people use for solid state, and this covers some of them and why they're important, what they're used for, and what they go into. And now, Jeff, I'm going to let you do sodium ion in
Real
1 or 2 minutes, and then Chloe, you get to do your section.
Yeah. Real quick though, in the solid state section, there was like you double the energy density, you get double the EV range. I really like that disproves it. The reality, guys, is aerodynamics is more an impact on vehicle range than mass. That's just kind of the fact, right? So if you throw in something with double the energy, if the aerodynamics don't change, you don't get double the range. That's just kind of how it works. So this is sodium ion. This is kind of like basically just going down to the main companies, Bedrock, RIP, Natron, RIP. Just kind of going through their shared pain points and kind of what challenges they faced, right? On the side of Bedrock, they basically just mapped out it wouldn't be economically viable, and Natron basically just ran out of funding. But the point being here is they're all sharing similar tranches. This kind of just goes down, as I said before, like lithium sulfur. Sodium ion is one of many subchemistries and what you choose to do in it. So a lot of the times the high performing stuff has cobalt in it, or it has some other thing in it, like vanadium. But this just goes down who's doing what and kind of who's the producers of those things and where they are. And then kind of this goes over kind of what the big issue is that, like if we assume a 10 gigawatt hour factory, because sodium ion is less volumetrically energy dense, and the good way to think about it is you can only fill so much liquid in a can. You need to make more cans, which means the cost is up because you have to use more cans to get the same total energy. And this is one of the reasons why Bedrock kind of mapped out and was like, this isn't going to work. It's just because the inactive components, you need a lot more of them to achieve the same total energy output.
Yeah, and it can be as bad as half for some of the chemistries here. And actually, there's some really cool stuff I'm going to take 20 seconds talking about real quickly, but there's some really cool stuff being done by Steer, Stanford, Slack, Adrian Yao that will be presented at the Volta 2026 conference in late February. Talking about a lot of this because they did an enormous amount of testing and teardowns of large commercial sodium ion versus LFP cells of these form factors. And again, I think the highest one was 230 watt hours, 230 amp hours in this can size, compared to with 280 or 300 for LFP. So sodium ion, 150 to 230, same size, same weight, compared to LFP, nearly 300. And that's a huge barrier to get through. They've been able to piggyback in sodium ion on the same manufacturing processes, equipment, all the other materials, and learnings to basically jump ahead really quickly, but it really comes down to the energy density versus the cost and the cycle life. And they're just not quite there to compete with LFP yet. And I think it will take probably changes in the actual
Aubert.
performance of the materials to do that. Right.
Yeah, let's just keep
Okay.
going through.
Sorry.
It's just yeah, this one just goes over the voltage range, right? And sodium ion has a wider voltage range. You can look at it here versus more traditional lithium ion chemistries, which is impactful. Keep going. And then kind of here's commercial sodium ion cells versus an LFP reference for people from the different companies. You can click on these and get them all as well. Keep going. And then this is kind of more sodium ion, they're emerging grids. We don't need to spend a lot of time here.
And that is the end of our presentation, Chloe. We turn it over to you. 60 slides in 35 minutes. Okay.
That's pretty good going, isn't it? I'm hopefully not going to have to rattle through mine so quickly. So I have slightly less slides. Let me just share my screen. Hopefully everyone's got that.
Yep, I can see it.
Perfect, thank you. So we've heard the battery industry is transforming pretty fast, faster than ever. And behind the innovation lies essentially a web of intellectual property, shaping who leads and who follows. So I'm going to rattle through patent trends, litigation, and hopefully safety recalls that are shaping the industry and how these forces can affect growth, partnership, and risk across the battery value chain. And hopefully leave some time for some questions at the end. So before we dive into the details, I want to take a step back and look at the big picture. So this slide captures the global patent landscape for batteries in 2025. What you can see here is a market that's not just growing, it's accelerating. That's driven by things like EV adoption, energy storage needs, sustainability goals. But what you can see is China is the clear leader. China has been driving the majority of patent filings, and it's reflecting its position as the innovation hub. And Asian companies generally are continuing to shape the competitive IP environment. Western filings do typically remain modest in comparison, but it's not just about the numbers. So it's about understanding where the innovation hotspots are, where we have things like freedom to operate risks, and how those trends are going to influence strategy in the years to come. So patents basically represent kind of strategic control over technologies that will define the next decade. And so understanding the trends in patent filings is kind of critical for anyone navigating this space. So if we start with like where the innovation energy is flowing, this chart shows patent activity by key battery innovation topics in 2025. We can see that electrolyte and battery management systems are seeing quite strong growth, particularly in the solid state electrolytes. But you can notice that there's a decline in anode and cathode filings compared to 2024, suggesting a shift from incremental chemistry tweaks to system level improvements. So, actually, despite sustainability pressures, recycling patents remain quite underrepresented globally. The takeaway here is that performance and safety are really driving innovation priorities. And then if we look at the evolution of technologies over time, you can see that the red line, that's lithium ion, that remains the backbone of battery innovation. But you can also see in the expanded diagram here that sodium ion has been the fastest growing technology since 2021, and that's essentially driven by CATL and Chinese R&D. And then redox flow, which is this brown line, has also been picking up in the last 5 years. Interestingly, lithium sulfur filings have kind of plateaued, and zinc ion, which is the blue line, though small, it's emerging, and that's currently being led by Chinese academic institutions. And so whilst small in volume, the zinc ion filings could signal some kind of early stage breakthroughs. Essentially, alternative chemistries are moving from niche to mainstream, but lithium ion is still going to dominate the patent landscape. We've heard from Aubert that solid state and semi-solid state batteries are coming out on the market. And we can see from the patent filings that Samsung, LG, ES, and Toyota together hold about, I think it's about 12% of the filings in this space. And you can see actually from the names in this graph on the right-hand side that in the top 20, there's a real clear automotive focus for solid state filings. And what's striking is that General Motors is the only non-Asian player amongst the top applicants, which kind of suggests that Western OEMs are at risk of falling behind in one of the most transformative technologies of the decade. For sodium ion, which is a tricky market to be in, CATL dominates this space. It's got more than 22% of patent families in 2025, probably a strategic bet to reduce reliance on lithium and diversify their supply chains. And notably, I think Toyota here and PPES are the only non-Chinese names in the top tier, again, kind of underscoring Asia's leadership here. Now, IP enables capital formation. It enables licensing, defensive market entries for next-gen chemistries, and it also frames like the collaboration we were hearing about earlier. With this kind of innovation racing ahead, collaboration evolving, then IP disputes are going to increasingly influence who captures value. So if we take a look at the litigation trends, we can see that IP disputes in the battery sector have become more frequent and more visible in the last 5 years. With multiple players working on comparable improvements in materials, chemistry, cell architecture, companies that are even acting independently can find themselves occupying very similar technical spaces. So if we take, for example, CATL versus CALB in China, that was a multi-year patent war involving 7 patents and damages nearing $95 million. And that was all to do with patents relating to specific lithium-ion technologies. And then in Europe, Tulip Innovation, which is an LG, ES, and Panasonic essentially licensing pool, Tulip secured a landmark injunction against Sunwoda for EV battery separator technology. And that was the first major injunction in Europe on car battery patents. So litigation action can be used to shape market positioning. It can clarify freedom to operate boundaries and also secure leverage in licensing discussions. If we take a look at another branch to IP litigation, there's recent trade secrets disputes. So Tesla versus Rivian, demonstrating that businesses are taking a more robust approach to protecting confidential know-how. Essentially, battery expertise is in high demand and businesses are aggressively competing for talent. When employees move, there's going to be questions inevitably around the boundary between an individual's expertise and a company's proprietary processes, which is why things like trade secrets disputes come into play. And then another branch to IP disputes relates to trademark and trade dress enforcement, which I think is becoming more visible than it ever has been. So we can kind of put that down to companies expanding into new regions, brand identity and marketing then becomes more and more important. And that's particularly true in markets where consumer awareness of battery brands is rising and competition is fierce. So we've seen a couple of key disputes in India, for example. And finally, I've got a couple of minutes. So safety. Over half of battery recalls in 2025 involved consumer electronics, particularly power banks. Some of the issues underlying those recalls included overheating, defects from welding, things like electrolyte leakage. And then EV recalls accounted for about a quarter to a third of the recalls, mostly linked to high voltage battery failures. And these kind of demonstrate vulnerabilities in design and the supply chain, which can demand stronger traceability and process control. So essentially, safety engineering and quality IP need to really advance in lockstep with the chemical innovation that we're seeing. So to wrap up, 2025 has been a year of rapid innovation and strategic shifts. China's consolidated its lead in patent filings. We can see that sodium-ion and solid-state technologies have been gaining momentum, and litigation is shaping competitive dynamics. These trends are highlighting an industry which is evolving at speed, and there's opportunities that we can take, but also risks move alongside those opportunities. Thanks.